Thank you. Chuck Brandel, I'm an engineer with INS Group. We have 7 offices in Minnesota, Wisconsin, and Iowa. Where we do our agricultural drainage work is kind of the green area, and I do most of my work in southern Minnesota. A lot of the work I do is for landowners and counties or drainage authorities. So we're going to talk about their perspective and how they look at projects and an example of how we can do water quality on an ag drainage improvement. So, why an emphasis on ag drainage? This is pretty obvious to everybody, but increased input costs, the demand to feed the world, the agricultural, in our area, the agricultural community is based, or our economy is based on ag. And the drainage systems that were constructed 100+ years ago are the backbone of this infrastructure. So why are we getting the pressure for a lot of improvements? We've seen huge increases in the amount of repairs and improvements. We have systems that are aging, undersized. You can see here we've got a picture taken from a state highway. This is in September after a large rain event. You can see the corn is 4 feet underwater. The system here was falling apart, not working properly, and we had pressure to do something about it, to either fix it or improve it. The other obvious things that we're seeing, 100-year-old tile filled with sediment. That's reducing the hydraulic capacity, causing blowouts. We have repairs that need to be done, and it's hard to repair a lot of these systems without redoing them. And when you look at the cost effectiveness of repairing a system like this versus improving it, changing the depth, changing the capacity, it ends up to be a no-brainer from the landowner's perspective to look at upsizing. Even this, showing a 100-year-old tile, I get landowners that say that this is in really good shape. When you look at the offset joints from its original capacity, each year that gets worse, and they can see 30 to 40% reductions in their capacity. So that's the pressure that we're getting to look at and improve these systems. Even the open ditches. This is the same system. On the left is before cleaning, on the right is after the cleaning. So on the right, that's what the system was designed for. We have buildup in sediment transport, tiles that are underwater, impairing drainage, sloughing, and all these things need to be maintained and or improved. So why do we look at storage and water quality? Political is a big thing. Politics, agencies, downstream effects. In Minnesota, the drainage law, you cannot improve a system or change the drainage characteristics unless the outlet is adequate. So you cannot flood those downstream. But in the drainage statute, it says outlet has to be adequate. We're seeing more demanding of system tiling, increased flow from more improvements. We're seeing new regulations on water quality, more emphasis on downstream flooding and erosion. Obviously, the Gulf hypoxia has a lot of groups are looking at ag as a problem to that. Southern Minnesota, we have a lot of stream bank erosion. There's debates whether that is geomorphological or caused by the tiling or both. So we have a lot of pressure to look at water quality and at what can be done for that. So how do we develop win-win solutions? Now, I started out saying that we get hired by the drainage authority or the landowners to look at a problem. How do we fix this system? How do we improve it? How do we drain the landscape better? And the key that I believe and has worked in many of the watersheds that we work on is education early, that there are other options than to just replace the old 8-inch tile with a 30-inch tile. Upsize, deepen a ditch by 4 feet, widen it, there are other options that can be done, and you can develop win-win solutions. So the landowners need to improve the 100-year-old infrastructure. They want to increase their drainage capacity off the fields, but they also need to be cost effective to make it work. Agencies and others, they want water quality benefits and storage. Sometimes they have funding available. It's not always the easiest to get, but there is funding available. And they need to understand cost too. That there needs to be a benefit for these landowners to do something, to move forward. And if you can educate them early on, develop a plan, get buy-in, you can have a system that hopefully is a win-win. So one way that we're doing this is called multipurpose drainage or multipurpose drainage management. And we're trying to do these plans up front at the beginning of a project, not at the tail end. Minnesota drainage statute actually changed. There was some rewording last year, and the term multipurpose drainage is now in the statute and needs to be part of any public drainage improvement. We've been doing this for quite some time, but now it's actually part of statute. So to break down multipurpose drainage, we break it down into 3 categories. Preventative. These are things that the landowner can do. Conservation practices that can be applied towards existing agricultural land without dramatically changing the layout of the landscape. So these are residue management, nutrient management, crop rotation, cover crops, all the things that are done on a field scale. Then we also look at control. In all of these cases, we're looking at an entire watershed. The preventative treatment can almost be applied anywhere in the watershed. There are limitations. But the other practices are more strategic. So we're looking at control practices that convey water, control flow, direction, rate, or maintain a desired water elevation. So some examples, water control structures, which is associated with controlled drainage, two-stage ditches, grass waterways, alternative side inlets. Here we have a rock inlet. We've also looked at multiple types of different side inlets. Other side inlet control, looking at how long can we store the water on the side of an open ditch without affecting the crops, but not straight, getting some water quality or storage benefit. Grass waterways, riparian channel vegetation, which is extending that natural channel with riparian vegetation or increasing the floodplain. And then on some of the more larger channels, looking at, instead of riprap to protect bends, tow wood sod mats and other alternative solutions. The third multi-purpose drainage management part is treatment. This is treating runoff and drainage water by providing filtering for the use of vegetated cover or water storage. Treatment and control, there are some practices that can be in either category. Some of the multi-purpose drainage management things we do for treatment measures, filter strips, wetland restorations, sediment basins, wood chip bioreactors, and saturated buffers. So when we look at a multi-purpose drainage management plan, we take the entire watershed, look at the areas that the landowner or drainage authority want to improve or repair, and then provide these solutions where they best fit, where they're most cost effective. And there's usually a little bit of give and take. There's always politics involved. Where is the best spot to put a wetland restoration or a sediment basin? You may not have the support to do that, but your number 2 or 3 areas, you may have the support to do that. So that's why identifying those areas, getting the priorities, and working with the drainage authorities to develop these solutions. We've got multiple examples of how this is done. Our biggest and brightest example is what's called Blue Earth County Ditch 57. This is a 6,000 acre watershed in southern Minnesota, about a half hour south of Mankato. The watershed line is shown here. It encompasses the city of Mapleton, which has about 550 acres. It was constructed originally as an all-tile system in the early 1900s. We actually found records of some tile that were in the late 1890s. And then in the 70s, the main portion of this tile failed, and a large open ditch was constructed, shown in blue and green. There was a compromise, and the bottom end of the watershed was improved with a pipe instead of an open ditch. Then in 2007, there was large failures in the system. We had some large rain events, and an improvement was proposed. Just going through a little bit of the history. This improvement wanted to increase drainage capacity, but the overall goal of the project was to replace the aging tile system, get the water off of the fields, increase water quality, and reduce peak flows. How did we get there? We had the multiple large storms, the 100-year-old design on most of the system, and there was a battle upstream versus downstream. Those that got the open ditch in the 70s said, we can't take any more water. And this system drains into the Big Cobb River, which is an impaired water. It drains into the LeSueur River, which is also an impaired water. And we had groups downstream saying, you can't improve this system. You can't add another drop of water into the system. It already has issues. So we ended up coming up with a compromise. The landowners originally petitioned for an open ditch and an 84-inch pipe to replace the aging system, and it was decided that storage was essential for the project, and we were able to downsize the outlet to a 54-inch pipe by adding storage and other treatment. Landowners also said, we don't want to pay for all of this. We think that there should be help to pay for it. So in the petition for improvement, it said storage was essential, and it had set a cap on how much landowners wanted to spend, which was about, in my mind, 10% of what we needed to actually do it and do it right. So we put together a multi-purpose drainage plan. We didn't call it that at the time, but we looked at the entire watershed, identified areas that we could do water quality storage paired with the drainage improvement. And then we went and found, we met with agencies in Minnesota. The Minnesota DNR is an important agency in reviewing drainage improvements. They loved the plan. They said, this is what we've been asking for. Got their support. And then we went for funding, which is, there was a sales tax amendment where funding went to help the environment. And the LCCMR, which is the Legislative Citizen Committee on Minnesota Resources, had funding available. We applied for that funding and got $485,000 to do water quality implementation and water quality monitoring. In all, the improvement project was about a $1.3 million project with $485,000 funded for water quality. None of the funding went to drainage improvements. It all went to water quality, monitoring, and design. So zooming in, you see all these squares. The red squares are areas where we monitored for flow, and the orange squares are where we monitored for flow and water quality. We had a lot of different things we were monitoring for, primarily TSS, phosphorus, and nitrogen. We were somewhat limited in how we could monitor. It was grab samples, but we had continuous monitoring of flow. A little bit more detail. This line here was the new 54-inch pipe. A two-stage ditch was put into the plan. An overdug sediment basin was part of the plan. A storage pond, and then a city storage pond. So there are two ponds that were part of this plan. And then we tried to do a wetland restoration down on the southern part of the watershed. We had one landowner on board ready to go. The natural basin took up two landowners, and one of them wouldn't sign on. So we had a plan that included a wetland basin, but we couldn't get that one implemented because of a landowner not signing off on it. So I'll go into some of the details on the BMPs. We monitored flow and in 2012, 2013, and 2014. Monitoring a 6,000 acre watershed that is quite flashy is very difficult. We know there are some limitations in our monitoring. The results that I'm going to talk about are just our straight data from 2013. We're currently working on a final report for this project. And all of the data that I'm talking about was from 8 rain events in 2013. We had 5 one-year rain events, 2 two-year rain events, and then a big 25-year rain event. So the first BMP that I'll talk about is what we call the Klein Pond. It was put on the Klein's property. That's why it's called the Klein Pond. What it consisted of was a 3-acre square pond. Now this was our number 2 spot to put this pond. Our number 1 spot was right here. And this landowner did not want it. We tried everything we could, offered them higher land easements. I had the commissioner supervisor talk with them, just couldn't get it done. So we moved our pond to this location here. And the way this works, the open ditch comes down, drains into the pond via a 48-inch pipe, drains out with a 15-inch pipe. So we capture all the flow from approximately 2,000 acres. The city drains in here. This picture actually north is to the bottom, just so to orientate yourself. The city had owned a pasture area that they kind of used for stormwater overflow. We were able to deepen that and provide a restriction. It had a 27-inch tile outletting it, and we reduced that down to an 18-inch tile. So we're slowing the water down from the city, but we're also slowing the water down from the agricultural watershed. This picture, we just happened to be flying aerial photos for an architectural project the day after the 25-year storm event. So I told our guys to go down and take a picture of the pond and see how things are working. This pond was excavated approximately 12 feet. Most of that spoil was put onto this field. This entire area used to be a shallow wetland or shallow lake before the ditch drained it. So there are very peaty soils in this area, and we bought an easement to fill this area approximately on average 4 feet. It hadn't been system tiled, and worked with the landowner to be able to just move the material to this location, which saved costs. Here's a picture shortly after the flood from a ground level standpoint. One other thing to mention, the reason the pond is in this location, this farm had given an easement to the city of Mapleton for their compost pile, and which was in this location, and we just tried to line it up. So essentially we straightened their field at this area. Picture after the flood, waters are receding. So just our straight data, and we're currently reviewing this, our percent reduction in peak flow, all we're doing is we're monitoring what's going in and what's going out. So what's the flow coming in, what's the flow coming out? For those 8 rain events, we had an average peak flow rate reduction of 77%, which we thought was great. And by doing that, we were taking grab samples and monitoring before and after. We showed a reduction of 47% in TSS, 63% in phosphorus, 60% nitrogen. Those are really good numbers. Our 2014 numbers didn't look that good, and neither did our 2012. They're probably about 10% lower. A couple things to quantify this. We surveyed the entire basin before any flow went into it. We're going to go back and survey. We have a sediment storage area that's built into the pond that can hold about 3.5 acre feet of water or 300 dump trucks of sediment. We'll see if our monitoring numbers match up with it, which is what's actually there. The pond itself, during flood stage, can hold 26 acre-feet of water. So the next BMP that was installed was a two-stage ditch. Here's the pond location. The two-stage ditch was just upstream of that, approximately 1,500 feet. For those of you that don't know what a two-stage ditch is, it's a channel within a channel. So a standard ditch is built 1.5 to 1, 2 to 1 side slopes, 4 to 10 to, I've seen 20-foot wide bottoms on open ditches depending on the watershed. On average we see 4 to 6. A two-stage ditch has a bench. It's trying to mimic a natural channel. So instead of a 4 or 6 foot wide bottom, we put in a 2 foot wide bottom on CD57. We put 10-foot benches in and then seeded all of this, including a buffer, with native vegetation. In theory, we're trying to get a lot of the wetted perimeter away from this area, reduce sloughing, and then during flooding events, provide some nutrient uptake with the bench. Also, if sized right, the channel should keep itself clean if you have a constant flow. This was the first two-stage ditch on a public system constructed in Minnesota. So here's a few pictures. We have a fall picture. You can see the flow area here. There are the benches. During flood, we did downsize the outlet to hold some water back, so it does also act as a storage basin. And then after a large rain event, you can see some of the sediment that's deposited along the channel. Coincidentally, a few miles north of CD57 is County Ditch 86. And this system hasn't been cleaned in a while, and we went and looked at it with the Drainage Authority. Said, boy, it's forming itself into a two-stage ditch. And should we clean that? And the consensus was, no, let's keep an eye on it. Let's make sure that we're getting good flow down the center channel. And hopefully, maybe in the future, we can get some money to monitor this. So how did the two-stage ditch perform on our 2013 rain events? I don't show flow here because from monitoring station to monitoring station, we're adding 550 acres of watershed coming in. So our flow increase, we had an increase in flow. So we just looked at the water quality components. For those 8 rain events, we had a 10.5% reduction in TSS, 8% reduction in phosphorus, and 20% or 19% reduction in nitrogen. Another BMP that we put in was a rate control weir. This was on the end of the system, way on the northern end, so it treated 6,000 acres. We had the channel deepened in this area. The slope on the channel is 0.1%, but in this area we have a very deep channel. It's very close to the natural outlet of the system. We put in a 5-foot high weir. You can see how tall the ditch is here. This guy is about 6'2", with a 1-foot opening. And we set the top of this weir. We did some hydraulic analysis, but really what set the top of this weir was the lowest tile coming in to the area affected was 1 foot above the top of the weir. So from the landowner perspective, they have a free outlet to their tile system, and we take this long, flat, deep area and we create 6 acre-feet of storage behind the weir. Here, other side of the channel, the weir bumps up, holds water back. We are close to the Cobb River, and what happens in this system is that the backside fills up, comes down, and then the downstream side comes up because we get backwater effect from the river at this location. Here's a hydrograph of the weir. This is a little exaggerated. This was our modeled existing flow, and this was what we actually monitored for the 25-year event. You can see, in theory, this area is stored behind the weir, and then we do start to see the water come back up from the backflow. So what's next for this area and other drainage systems that we're working on? Continued education that these things will work. We see, working with landowners, that they want to see an example of something that works. Showing the picture of the flooded basin and the field next to it, not flooded. There was a little bit of flooding on the other field adjacent to it. That landowner got, I think, 240 bushel per acre corn that year. Showing those examples goes a long way in getting these projects moved forward. We're seeing a lot of these type of projects. And it just depends on what's available in the watershed, how much money can we spend, and where are the best places to do it. So we're trying to continued education, implementation of more pilot projects, and then continued monitoring. Our grant ends June of this year. All of our monitoring is done. We're finishing our final report. We are now working with the Minnesota Department of Agriculture and the MPCA to continue this monitoring and maybe even improve on what we've learned. We lost cameras, we lost monitoring equipment. We do understand that grab samples, we're not catching the entire storm event. So we're looking to improve our monitoring by doing continuous grab samples. And we've got a 3-year plan to continue this monitoring. So that's all I got.
Very good. You want to take a question or two as
Sure.
it's set up?
Yep.
What elevation, or how are you determining the elevation of your bench?
We did this design quite a few years ago, and we just took it at 2 feet. We now have a better formula of how we would design that based on the watershed area and how much flow we have in the channel. What we're trying to do is have a base flow that fills the center channel. But in this case, we just took 2 feet because that was the standard cross section at the time.